Hey guys, today we're going over the classic embedded systems firmware interview question. This is the one that you should know front and back. It's the most basic one that majority of interviewers are going to default to. And this is the ring buffer problem. So essentially the objective is to implement a robust circular buffer for a resource constrained embedded system. And so this is typically going to be used to pass data between an ISR interrupt service routine and the main loop maybe on your embedded microcontroller. So the ISR is going to be getting data through an interrupt driven sensor maybe, and that sensor through the ISR is going to be populating data into this shared memory buffer, and then your main loop maybe is going to be reading that sensor data from that buffer. And so this will allow a producer-consumer type of solution to the issue of reading sensor data. And so let's get right into some of the different ways that we can go about coding this. Let's just talk through it. So just going back through the problem, so we need to initialize the buffer, implement the push logic, implement the pop logic, and ensure that we update these struct values after every operation. So yeah, like I said, this would be used as a bridge between ISR and the main loop. So we're doing the pushing in the ISR, and then we're doing the popping in the main loop to read the data, right? And so just to kind of visualize what this looks like, let's go to our visualization here. So hopefully you guys can see it all right. But we have, so this is a kind of example. So let's say we have an array of 8 elements. That's going to be the data storage portion of our buffer. And then we have these 2 pointers. We have the head, which is where we're doing the popping from. And we have the tail, which is where we push data. And then you can see 0, 1, 2, 3, 4, 5, 6, 7. So this is just kind of the index of the elements. So essentially how this works is that, let's say the ISR reads sensor data. It'll push data to wherever the tail is. So for this example, they're both starting at the 0th index. So we're going to push data. So the data will get placed in here, and then we're going to increment the tail to the next element, and then maybe we push data again, increment again, so we have data in the 0, 1 indexes, and then the head starts still at 0, it's going to pop data, and then move, and the next time it wants to read data, next time the main loop wants to read data, it'll increment again and move down here, right? And so why it's a circle is so to basically handle the conditions where we maybe run out of data or run out of storage. So let's say we push, we haven't popped anything, right? We push all the way till here until we're full. Essentially, depending on how you want to implement the buffer, you can just keep pushing data and increment this pointer, right, using a modulo operator around to the next 0, and then start overwriting if you want. So if you really wanted to, you could overwrite the oldest data. So this might be if like you want for the freshest sensor data and readings, then you just overwrite the data in the 0 and keep going. And so you don't need to worry about running out of space. Obviously this isn't ideal because you're having to discard data that you stored, but this is kind of a way to handle that. And so for a fixed length array, we can kind of just keep pushing data without worrying too much about running out of memory. If that's okay, if that's an okay way to handle the overflow. So there are other ways. So basically, like maybe if you realize that you're full, another way to handle it would be to just stop until the head increments. And then once the head increments, you can push another data piece onto 0. And so we would have the most up-to-date data here, but we haven't overwritten any data. We just waited for the head to pop. So it kind of depends on how you want to handle that. That's going to be on a use case by use case basis. So yeah, there's really those two. That's for how to handle the full, and then basically how we want to handle empty is essentially it's usually going to be if the head and tail are in the same place, right? Yeah, or if the count of elements in here is equal to 0 if we're maintaining a count. We can do that. Also, there are other ways that we can get into, and there's actually another way that I'm going to implement the solution. So instead of maintaining the count, I am going to do this without the count value, And what we're going to essentially do is if you don't have the count, it's hard to distinguish between the empty state and the full state, right? Because in both cases with the count, these tail and head would be the same index. But I'm going to basically do the method where you leave a empty data array or data slot here. So we don't fill this last index up, or we always keep one index that's empty essentially. And so what this allows us to do is it ensures that the tail and head, when we have all the other 7 storage elements filled up, it ensures that they have a different index. So we can tell when there's this difference here between tail and head indexes that we're full. And then when we're empty, the tail and head will be at the same index. And so we have 2 different delineations so that we can tell between the difference between empty and full, right? Because if we just filled up all the elements, then this would, tail and head would be in the same place when it's full, right? Because you fill up all 8, and then you increment the index, and they're back again. So, and that's the same as when it's empty. So let's implement that solution. And yeah, let's get into the code. So essentially, I'm going to implement these, the solution, and we're going to take out count. So we don't need count for this method. So there's obviously the downside of we have 1 less memory element, but in my mind, I like that we're able to simplify. And in this case, it's a good trade-off, right? Because the size t count is going to be a 64-bit value, and our circular buffer elements are only 8 bits. So we're essentially sacrificing 8 bits to save 64 bits, which is a good trade-off in my mind. So let's go ahead and init here. So let's go init. So what we're going to do is to initialize our circular buffer, we're being passed, so the memory is allocated by the caller. If you watch my previous video, you'll see we talk more about the caller being responsible for allocating memory, but init, we're going to init the memory for the circular, we're going to initialize the memory for the circular buffer outside, and then we're going to pass that into this init function to initialize that memory to certain values. So it's not just like default empty memory. So obviously if the circular buffer pointer that's passed to us is null, we don't want to do anything, right? We need a good pointer here. And then cb buffer, so we have our different members here of the struct. So the buffer is the actual data array itself. So we're going to point that to the memory. And then we're going to say circular buffer capacity, right? That's going to be equal to cap. So just initializing things here, nothing crazy. And then the head index is going to start at 0, and we're going to initialize the tail index to also start at 0. So looks good to me. Let's move on. So how do we want to push, right? So we need to check if we're full. So let's start by checking if we're full. So how are we going to do that for our implementation? We're going to see if the tail is 1 index behind the head, and that's how we'll know if we're full. So we're going to say, essentially to check if we're full, we're going to need to see if the next pointer is equal to our head, circular buffer head, right? Because the next, if it's equal to the head, is essentially how we know it's going to be full if we push data again, right? But to get that next pointer, essentially to calculate the next element, what we do for this solution, like I showed you in the graph, right? We want to see if the tail is 1 behind the head or 1 behind the max capacity. We're going to do CB tail plus 1 mod capacity, and I misspoke, sorry. This is just to get the next pointer, right? But to check if it's full, that's when we compare against the head pointer. So that's next. And then what we need to do is if next is the head, then we're going to be full. So we're going to return circular buffer full. So we have these nice states that we're going to be passing from our functions here. And then essentially here, if it's not full, then we want to add data, right? So I don't want to overwrite the old data for this solution. I'm not going to be doing that. That's another implementation that you could do. If you have a clean way to do that, throw it in the comments. But essentially, to add data, I mean, should be pretty straightforward, right? We're just going to, inside the data buffer, at the tail, which is where we're adding data, we are going to give it the data. And then we also obviously need to increment tail to next, right? And then we're going to return circular buffer is okay. Okay, so let's move on to our pop. So we also are going to check if empty and retrieve data from the head and tail index. So to check if empty, this should be, what do we think, guys? So to check if we're empty, we already talked about this, right? Head and tail are in the same place. So we're going to say if CB tail equals CB head, right? Return CB empty, and we don't want to, because we don't want to push, we can't pop anything if it's empty, right? And then if the data inside the memory, or if data being given to us is not a null pointer, so we're returning the data out through the input parameters, right? So if the data is not null, then we're going to say the value at the data pointer is equal to our circular buffer, and then we're indexing CB what? We're just indexing the head. And that looks pretty good to me. And then we want to say, we also then need to increment the index, right? So to increment the head index, what do we think we want to do? So CB head equals the current head plus 1, right? And then, like I said, for circular buffer, we wrap around. And so we're going to mod the capacity, just like we did with the tail. And we get to return CB is okay. So now let's think a little bit more through this, right? So we have two separate processes that are each accessing some shared data, right? So the push, which is what the ISR is going to be running, is going to be accessing the head and tail. And then we also, and it's modifying the tail, right? And then the pop, which is what the main loop is running, is going to be accessing the head and tail also. And it's going to be modifying the head. And so in embedded systems, what we want to do is if we have two separate processes, two or more processes accessing shared data, we want to make sure to tell the compiler that these are volatile. So these are the head and tail, which are volatile. And then if we had a counter also, or a count value, then that would also be volatile. Right? So essentially, a volatile is you're telling the compiler to never cache this variable inside of a register. So essentially, we want to tell the compiler that this value is going to be modified in the shared memory region. It's not solely modified in our process. And so because it's being modified in the shared memory region by another process maybe, it could be updated. And so we need to make sure we go all the way out to main memory to access that value, instead of just being in a local register in the CPU. So that looks good to me. Let us go ahead here and let's run this and run the test. Everything looks pretty good. and boom, all tests passed. So we push and pop and checked if the buffer was full. All right, thank you guys. Hopefully you learned something here. Leave a comment if you have an idea for another problem you want me to cover and talk about. Yeah, see you guys next time.